Okay, so thank you very much. So it's my pleasure to be here. Thank you, the organizers. So I'm going to talk about testing expansion. And so the goal of this talk is to see how can we distinguish between good expanders and poor expanders. And in particular, the main result is that in time proportional to square root of n, we can distinguish between good expanders, poor expanders, and everything is the framework of property testing. Now, if you could ask, okay, but why do I want to talk about here? In fact, technically, the main challenge is how can we analyze some random walks in graphs which are not expanders? Okay, or in some way, how can we show that if we have a graph which is non-expander, that the random walks will be slow? Now, here's just one more thing. So this time square root of n. So I'm from computer science, and somehow I would like to come back to the question raised yesterday or comments about computer scientists. We do care about exponents. So it is easy to solve this in polynomial time. Here the main challenge is we want to do this in much better than linear time even. Okay? So what is really the scheme of this talk? So first I want to explain to you what is really property testing framework. Then I would like to tell you something about challenging question, what is known. And then I will give you some sketch of the proof of this result. First, just to make sure, we want to study expanders. Expanders are graphs which expand well, which means if you take any subset of vertices, this subset will have big neighborhood. Okay, so we want to do this in framework of property testing. So in general, our task is as follows. So we are given an input. In that case, it will be a graph. And we would like to say, okay, we would like to accept graphs which are expanders. And we would like to reject graphs which are epsilon far from expanders in some special way, define notion of epsilon far, and we are allowed to err with some small probability. Okay? Now, here in general, the notion of being epsilon far does depend on the problem at hand. So it's really very problem specific. You'll see some definitions soon. In general, this should mean the following thing, that if I have representation of my input, okay, so graph, for example, will be epsilon far from being an expander. If I have to modify my representation of the input of epsilon fraction of the elements to obtain a good expander. Okay? Now, usually we'll be thinking that epsilon is a small constant. Okay, so in some bounds I will actually ignore epsilon in big O notation. Okay, now I would like to give you some more feeling what does mean that we are epsilon far and why this is useful in computer science and not only in computer science perhaps. So you know, we would like, so if you look at this graph and we are asking, is this graph connected? We would like to say, yes, it is this graph is connected. This graph is also connected, even though one of these graphs is not connected. Okay, so, but I would tell you somehow this is the motivation. If you have a graph with 1 billion nodes, okay, and if you have some isolated node, the graph is still almost connected. Okay, so we're quite happy with this, but would like to, okay, but would like to reject graphs which look like this. Okay, so our goal kind of is to distinguish between, you know, black and white. You are either pretty well connected or you are very disconnected. Okay, now, so we have to define our model more formally. So there are two classical representations of graphs, as you know. One is adjacency matrix. So we're given a matrix which represents a graph. So this graph means, you know, I have an edge between vertex number 2 and vertex number 1. So this is one graph representation. In that case, we would say graph is epsilon far from satisfying some property if we are allowed to delete epsilon n square edges, or we are allowed to modify our representation, adjacency matrix, in at least epsilon up in epsilon fraction of the entries. Okay? Now, of course, if you think about it, this is of course suitable only for dense graphs. For planar graphs, it's usually boring. Okay, so for example, if we want to study anything like, say, planarity for these graphs, most of all planar graphs are sparse. So if we are saying, you are allowed to remove epsilon n square edges or add, then the only thing you really have to do is you have to check what is the density of the graph, how many edges you have. If graph has less than epsilon n square edges, the graph is certainly close to be planar. Okay? So this is good for dense graphs. Now what about planar graphs? We have this another representation, adjacency list or incidence list, which of course, for every node we know all the neighbors. This is very good for sparse graphs, and that's what I would like to study here. Now, what people usually study in this setting is that we want to study graphs of bounded degree. So we are not studying just sparse graphs, or we're just saying, okay, each graph will have maximum degree bounded by, say, d, where d will be usually a constant. Okay? Now, I have just 2 slides or 3 slides about the adjacency matrix model still to tell you that that's still an interesting model. So we know a lot about this first model, adjacency matrix. So we know that there are very, very fast property testing algorithms. And essentially, I can show that all property testing algorithms are just following this very simple scheme. So what do? You just randomly sample a set of vertices. You look at the graph induced by these vertices, and you are testing the property. Okay? The algorithm is trivial. The analysis is usually very hard to show that you can test with this algorithm some property. And a few years ago, Allen and Shapiro, after a sequence of papers, they finally proved that every hereditary property of graphs can be tested in constant time. So if you think any hereditary graph property, you have an algorithm which will test this in constant time. What does it mean? That in this algorithm, this random set of vertices will be of constant size. Okay, constant size assuming that epsilon is a constant. Now, how big is this constant? So usually the bound that you'll get are, it was a challenge to write this in PowerPoint. But anyway, this is a very big tower. So actually this is a couple of towers. I think 3 is typical number of towers. So what does it mean? If epsilon is equal to 1/2, okay, this is much, much more than number of atoms in the universe, whatever. So it's a constant time, but still it's a very big constant. Okay? Good. So this is what we know about this adjacency matrix model. Now I would like to study this other model. So once again, bounded degree graphs, upper bound by d, where d is a constant, and unfortunately we know much less. Okay, we still don't really understand this model well. The main reason is perhaps that in adjacency matrix model, what people are really using is, I didn't mention this. So all this the fact that you have this constant time 2 towers of, it's just because you're using similarity regularity lemma. So you have some beautiful tool, combinatorics, which is, once you have it, people are getting results quite quickly. Once you understood that there is a connection. Now we don't have such a tool for adjacency list model, but so the reason we don't have is because we don't have this combinatorics, but we have some tool which is random walks. So in this algorithm, very often you are using random walks approach. Okay? So I'll just give you one example. So the problem of testing if graph is bipartite. So there is a very nice algorithm for this problem, which was given by Goldreich and Ron, which is working in something like square root of n time. And the algorithm is doing the following thing. You randomly pick a number, 1 over epsilon vertices. Now from each of these vertices, you will start some like square root of n random walks. Each random walk is of logarithmic length, polylogarithmic length. Okay? And then what you are doing is you are analyzing the graph induced by the edges that you visited. And if in this graph you will find an odd length cycle, you reject the graph, because of course the graph is not bipartite. But if every cycle you found is of even length, you would just accept the graph. Okay, so the algorithm is perhaps not difficult. The analysis was very difficult. So I think really the final analysis was, I don't know, 20 or so pages. And the main reason is they really want, I mean, Goldrash and Ron, they were studying what is the relation between this mixing time and somehow random walks in arbitrary graphs and the fact that you have lack of odd length cycles. Okay? Okay, so have Goldrash and Ron. Then they also show that you cannot really do it faster, so you really need square root of n time to check if graph is bipartite. On the other hand, as you know, we have these constant time algorithms in adjacency matrix model. In that case, actually, this constant is really small. Okay, so just 1 over epsilon square or so. Okay? So there are kind of two messages here. First of all, in this model, it's difficult to get constant time algorithms. Okay, and actually very few problems have constant time algorithms. And the second thing is that here we are really using this random walk approach, and the fact that we still don't understand some of properties of random walks is the reason that we don't understand this. We don't have better property testing algorithms in that setting. Okay? Okay, so the main goal here was want to test if a graph is an expander or not. This is kind of more like motivation. There are two reasons why we wanted to study it. First was many property testing algorithms in this setting were using expansion as the key property. Another was some people posed this as an open question. So Goldrash and Ron then actually showed that you need at least square root of n time. And you need it even in the case if your graph, so if you want to distinguish between an excellent expander and graph which consists of few disconnected expanders. So you really need square root of n time. So the question is, can you do it in square root of n time? And, okay. So, and you will see in a second that you can, somehow just to make sure that you know what we are talking about. So there are two definitions of expansion. One is, of course, combinatorial, which means expander is a graph without small cuts. And algebraic, which means if you look at Laplacian, the gap between the first and second largest eigenvalue is, now, when initially people were studying this problem, they were studying algebraic expansion, and I believe this was actually the error. So I think conceptually the main contribution is that we want to forget about algebraic definition. We want to switch to combinatorial definition. It is just more, excuse me?
Graph with a small segment.
Excuse me?
Expanded graph with a small segment.
This is the adjacency matrix.
Oh, he's doing the generator, the continue.
Yeah.
It's large second, smallest. You can't have
The gap, okay, this was about the gap. Okay. Now, so conceptually, in our proof, the main conceptual contribution is we switch to this combinatorial definition, and then some things are easier. Now, this is an algorithm, and as you see, algorithm is using random walks. So what we are doing is we are sampling vertices. Now for each, so we are sampling so many vertices. Now from each vertex we are doing the following thing. We start very many random walks. All random walks are of logarithmic length. Okay? Then we are looking only at the endpoints of these random walks. Okay? And we are looking how many collisions we'll have. Okay? For how many pairs of endpoints they will be the same. If this number is small, we'll accept the graph. If this number is big, we'll reject the graph. Okay? Now just to make sure, even if we are saying the graph is of maximum degree d, we'll always have this kind of random walks on regular graphs. So lazy random walks, so we'll move to a neighbor with probability 1 over 2d. Okay, so what is the motivation? Why this makes sense? So the main thing is, as we all know, if you have random walk, if you have expander, regular expander, then you'll have very rapid mixing. Okay, what does it mean? After O of log n steps, after all of log n steps, you will reach a random vertex. So now we would like to think, what does it mean that we will reach a random vertex? So we are just looking at this endpoint vertices on this random walk, and we want to check if the distribution of this vertex is uniform. Okay? The one way of doing this, you are just looking how many collisions you will have. Okay? And of course, if you run c times square root of n random walks, then we expect that the number of collisions will be something like that. So we know how many collisions we should expect. Okay, and right now we would like to just argue, okay, so if we have an expander, we know somehow how many collisions we should expect. And now we want to think what to do with other case, if we're not in an expander. So the key thing is, we'd like to prove that if graph is epsilon far from expander, then for many vertices, the random walks will not mix. Now, one slide with the history. So Goldreich and Ron, they actually suggested that algorithm, I don't know, 8 years ago. They had very nice paper where they just say, okay, we conjecture this algorithm is good. They didn't really know how to analyze it. The reason is, we understand, say, random walks on expanders very well. We don't understand what to do with non-expanders. Okay. So just to make sure, we'll be talking about vertex expansion, though in bounded degree graphs it doesn't really matter because vertex and edge expansion, they differ by d at most. Okay, once again, Goldreich Ron analyzed algebraic. We will analyze this vertex expansion notion. And the result that so our goal is to, this is perhaps another thing. We don't really want to distinguish an alpha expander from a graph which is far away from alpha expander. We're making some more relaxation. We're saying we want to distinguish between alpha expanders and graphs epsilon far from alpha star expander, where alpha star is much smaller than alpha, unfortunately. Okay? So first I will just give you some, I believe, not very complicated arguments how you can get this alpha star of order alpha square over log n. And then I'll just mention briefly how this can be improved. Okay. Oh, this is just to show you the bounds. So these are exact constant to that hopefully you believe me that it's true what I'm saying. Now, it is, as we said before, it's really easy to argue that if graph is good expander, then we'll accept it with high probability. Okay, so really the main goal is, what is if the graph is not a good expander, and want to argue that we reject it. Okay? So we have a key property, which actually perhaps seems to be very natural, but people before actually were trying to prove it didn't succeed. So the property is as follows. So you have graph which is epsilon far from an alpha star expander. And then we can find a large set of vertices which will have small expansion. Okay, so we'll have a set of vertices x, which is of size between, say, epsilon times n and 1 plus epsilon times n half, so that the neighborhood of this set will be smaller than or equal to that number. In my talk, whenever I'm using c, c star, everything, it's a constant, appropriate constant. Okay? Now, how you should understand this, if graph is far from being an expander, we always have a large set which will have very few neighbors. Okay? This is because, so this alpha star, alpha square and log n is just coming from my definition of alpha star. Okay? Now, how we want to use it? So this is when we are using some easy properties of random walks. So suppose that alpha is a constant, and let's just suppose that we have some set x with such a neighborhood. At most, c over log n times the size of the set. And suppose we are running random walk of size c log n half. Okay? Now, if we start this random walk at a random vertex from x, okay, then somehow, because it's stationary, so random walks, they always have, if you start at a random vertex, then random walk is an expander, it has stationary distribution, which is uniform distribution. So somehow you expect that after C log n half steps, you will visit C log n half vertices. But because of this constraint, you expect that with constant probability, you will not leave set X. Okay? So here's kind of perhaps, so if you are here and you are saying, oh, start at a random vertex, because this neighborhood is very small, and because you are starting random walk at a random vertex, if you perform number of steps which is smaller than the ratio of size of this over the neighborhood, you will not reach you will not leave the set X with constant probability. Once you have that, you can argue that because with constant probability you will not leave set X, with constant probability you will have much bigger chance that you will hit vertices from set X. So at the end you will have much bigger collision probability. Okay? Okay, so then we'll reject. So how we can combine this? So once we can prove that we have large set, with constant probability we'll start at a random vertex from that set, then with constant probability we'll have bigger collisions, so with constant probability we'll reject the graph. That's kind of the whole line of arguments. Now, depending on your mood, I will give you very briefly sketch of this proof, how to prove this. So we kind of are able to show that if you have a graph, any questions? Okay, so if you have a graph and you have any set A, which is small, okay, so that so that G minus, graph, if we remove this set A, is a good expander, okay, then we can argue that the original graph is not epsilon far from a good expander, okay. The intuition is somehow here. If you have here this small set, okay, and you know that this is an expander, then the entire graph cannot be too far from being an expander, okay. And the proof of this is, as you could expect, you can just argue, okay, we can modify epsilon fraction of edges. So if you have such a graph, you just modify epsilon fraction of edges, and you will get a good expander. Okay, and here is actually how you modify it. You remove all edges. So this is this set A. You remove all edges incident to this set A. Then you put a very good expander inside set A. Then you put some random matching between set A and the rest of the graph. And then you can prove that this will be a good expander. Okay. Once you have this result, you can kind of put it so that you first start with a small set of vertices. If this is already big enough, then this is your outcome. If this is small enough, you put this on side, you consider the rest of the graph. You have graph which has small size, small expansion, so you put this together, and at the end you will get this key property I promised to you. Okay. If you put all this together, you can put the parameters together to show that we can distinguish between graphs of maximum degree D that have alpha vertex expansion and graphs of maximum degree D which are epsilon far from graphs with such an expansion, and this is our running time. So it's something like d square log n root of n over alpha square epsilon cube. Okay. Good. So once we had it, we publish it. Then very soon people actually were asking the question if we can get rid of this logarithmic factor. We didn't know how to do it. Then first Kale and Seshadri came up with an algorithm which was able to, which was running in square root of n time, and was able to do this, so was able to distinguish between alpha vertex expanders and alpha square over a constant vertex expanders in times square root of n, but they had some major I think this was not, the part which we didn't like was that they were saying the beta expanders could allow to have big degree, 2D. Okay, and soon later actually this also was removed. So right now there are two papers, Case, Shahadri, and Nachmias and Shapira, who are kind of showing that in time root of n we can really distinguish between alpha expanders and alpha square over C expanders. And the main, similar results are do hold for algebraic expansion, but they are much weaker actually, unfortunately. The main trick is really that they are able to modify our proof, that you always have one big set with small expansion to make sure that you can actually construct such a set so that actually many vertices, you can argue, will have very slow mixing time. So the analysis is kind of tighter, more. Okay. Good. So to me, the main open questions are really, there are perhaps two. How can we understand, how can we say something interesting about non-expanders? And actually still understand random walks of graphs which don't possess some property. Okay, in order to use random walks to detect, graph that shouldn't be planar, so do something and then you'll get proof that it's not planar. Thank you very much. Yes.
So you still have some extra log factor, right?
No,
I mean,
this they don't have
log
log.
square root n.
Yes.
So the exact question by Goldreich and Ron was.
No, they didn't care about polylogs.
Computer scientists don't worry about polylogs, right?
That's a new position.
So the current best upper
So
bound
we
is
don't
one.
care about exponent. We do care about exponents. We don't care about polylogs.
So the current best upper bound is n
Upper bound
square root n.
square root of n times some polylogs. I don't know. It's not really. I don't think people consider it so important.
I have a question.
Yeah.
It might be a stupid question. Is there any hope of actually making the alpha squared over C alpha?
Yes, but very tiny,
What?
very small. Hope.
I mean, it's not the case that that's ruled out for some theoretical reason.
Not that I know about. But I think people think it's infeasible, but no proof.
Anything else?